Okay, so we're starting Unit 4, which is Work and Energy, and that encompasses Chapter 6, which is also entitled Work and Energy in your book. Um, so the real kind of key areas we'll be talking about is what is work, um, how is work and energy related, and the different types of energy there are. How do we conserve energy with the idea of conservation of energy, and then what is power, and how does that relate to work, and how does that relate to energy? So when most people use the term work, you think of working on a problem, going to work. That's more the colloquial sense of the term. But in physics, the scientific term work is when we take and apply a force to some object, and then that object moves in the direction that that force was applied. So work, in simplest definition, is force times a distance. Um, and the unit for force times a distance, was newtons times a meter, is going to be known as a joule. And we're going to denote that with a capital J. So as an example, if you have a person who pushes a box across a floor for some distance, they're going to perform a certain amount of work in that process. And the unit of the joule is named actually after James Prescott Joule. What he actually did his research on was trying to make an equivalence between how much energy in terms of mechanical energy was related to how much heat was being stirred into water. We'll talk about the heat aspect of the joule later this year when we get to the heat units. And one key thing about work is that it's a scalar quantity. So force is a vector, displacement is a vector, but when we multiply two vectors together, in certain cases, the resultant is a scalar. There are two different concepts in math. One's called a dot product, and one's called a cross product, sometimes referred to as a scalar product or a vector product. You'll learn about those again when you do vector math in your math courses. But here we're doing a dot product or a vector or a scalar product, which will yield that. So 1 joule is actually a very, very small amount of work. So to do 1 joule of work, you would take a medium-sized apple, so that 1 Newton apple, and we'd lift it a height of 1 meter. Okay. Now, if I just am holding an object, so I could have a very heavy object, so something that has a weight of, say, 100 newtons, and I'm just holding that object still, if there's no displacement, then there's no work being done. Okay. Now, what you might think, well, if I'm just holding like a large suitcase, well, my arms eventually get tired. Well, the reason for that is if you get down to the small level of your muscles are constantly contracting and releasing. So there is a displacement when you get down to the cellular level of your muscles, which is showing work being done at the cellular level. But in terms of like the large scale effect of me moving that across the room, you don't see that object having work done upon it. So to get into this idea of, again, work being force kind of times a distance, it has to be a force component in the same direction as that displacement. So we start to think of it as work being FD cosine theta, so that we're only dealing with the component of the force that's in the same direction as the displacement. So some people write it as work equals force cosine theta d, or just FD cosine theta, if you're just thinking about the component of the displacement in the direction of the force, because you can think of it either way. So imagine when you're pulling a piece of luggage that has those little rolly wheels at an angle. Well, only a component of your force actually pulls it forward, because some of your force is pulling up on it. And that component that pulls it forward would be the F cosine theta over that displacement. And that's the work that's actually being done in that same direction. So now work, it can be positive, it can be negative, and it can be zero on an object, based on this idea that force and displacement are vectors. So if the force and the displacement are relatively in the same direction, or the components are, so imagine that you've got angles that match up between the displacement and the force that put it in the same direction, you're going to end up having positive work being done on that object. However, if the force and the displacement are perpendicular to each other, no work is done. So an example of this is the moon. The moon is orbiting around the Earth. Well, the force is pulling it towards the Earth, but its displacement, even though it's going to go in a curved path, which we'll talk about circular motion a little later this year, even though it goes in the curved path, it's perpendicular. So the displacement is at 90 degrees, so there's no actual work being done on it. If your force and your displacement are kind of opposed, so you're pulling opposite the direction of the displacement from a force, it's actually negative work. So imagine this case is like brakes. So the car is moving forward, but the force is in the opposite direction. So in that case, that force is doing negative work on the object. It's taking energy away from the object. So another great thing about work being scalar is that we know that scalar quantities kind of just add together. We do know that forces as vectors can be added together because vectors add. But it becomes a lot easier. There's no idea of having to do vector addition. It just becomes pure addition. So once we find a work from a force, we can find out, force 1 doing work, force 2 doing work, force 3 doing work. We just add those works together to get the total work being done on an object. And that becomes the net work or the total work that we have for that object. Now, some people do it by finding individual forces doing the individual work, or some people find the net force and say that that net force does a net work. Both ways will yield the same answer. So when work is done on an object, it's going to change the object's energy. Okay? And this is a key thing, that there's a difference between work and energy. So work is the act of changing the energy of something. Energy is kind of a property of the object. So an object has a certain amount of energy. So when you push on a shopping cart, your work is going to go into increasing that cart's kinetic energy, or the energy of motion. That's what kinetic energy is. Kinetic kind of means motion. Energy is going to be that property it has now that it's in motion. When you climb a mountain, or if you take a book and put a book from the floor up on a shelf, you're going to be changing that particular object's, or or if you're the person climbing the mountain, your gravitational potential energy. Because potential energy, which is some various forms of, is energy that's related to a position or conditional change. So in the case of changing your height, you change your gravitational potential based on height. We'll get into talking about springs, which I know we briefly talked about the force of a spring during the last unit, but we didn't do much with it. Well, now we're going to understand a little more about why we cared about it, how it relates to things like mousetrap springs in this unit, with how it can store energy by its change in position. So the kind of key piece between work and energy is what's called the work-energy theorem. And work-energy theorem basically states that any type of work done on an object can change its energy. And the most classical kind of approach to this of the work-energy theorem is saying that the total work done will change the kinetic energy of something. So work equals delta KE. And we can actually use this idea of work equals delta KE to prove the equation for kinetic energy, because we're going to say right now that delta KE happens to be 1/2 mv final squared minus 1/2 mv initial squared here. Well, where did that come from? So we're going to go through a little bit of a proof here. So let me kind of flip over to a little drawing screen. And we had just said that work was equal to basically a force times a distance. All right, and by definition, we know that any force is a mass times an acceleration. So we have mass times acceleration times a distance. So right now, we can say that work is mad. Now, if we were assuming 1D motion, we can think of displacement, though, as a change in the x direction. That's where our displacement is going to be. So if we think back, we've seen this before. We've seen a delta x show up in one of our equations. Matter of fact, it showed up in the Vf squared equaled V initial squared plus 2a delta x equation. Okay? And if I rearrange this, I find out that V final squared minus V initial squared equals 2A delta x. And I can bring the half over. So I have 1/2 of V final squared minus V initial squared equals A delta x. And if I distribute that half in, which I'll do after I make my first substitution, we'll see where kind of the kinetic energy piece comes from. So what I'm going to say now is that work is equal to MA times 1/2 of V final squared minus V initial squared. And I'm going to distribute this in. So I end up with 1/2 M. Oh, sorry, the A is not really there. That's just like a multiplication because the A delta x is this whole thing. So 1/2 M V final squared minus 1/2 M V initial squared. So there is this idea that 1/2 mass a velocity squared minus another 1/2 M an initial velocity squared. So as we can see, the work will be equal to a change in what we're going to call kinetic energy. So we're going to define Ke at any given point in time as 1/2 mv squared. Okay. So that's going to be a really key piece for us as we go through this, trying to understand different types of energy. So now we know what kinetic energy is. So that kinetic energy will be the energy of an object just due to having motion. And if I go through the math of saying, well, I've got mass times distance squared over time squared, that's still going to come out to be a joule. So kinetic energy still in joules, just like work was in joules. So 1/2 mass times velocity squared is what we're going to define as kinetic energy. So the sign of the work, we need to remember here, is related to the change in the energy. So if the total work is positive, our energy is increasing. If the total work is negative, then the energy is decreasing. If it's 0, there's no change in energy. Okay. So if I was doing work on a car that was positive, the car should speed up. It should gain kinetic energy. If I was to hit the brakes, which is going to be negative work because the force is opposite to the displacement, the car should lose energy. It should slow down. It should lose kinetic energy. If there's no gas being hit, no brakes, no air resistance, nothing, I'm just kind of maintaining going down the highway, I should have 0 change in energy if there's no work being done. So now we get into this idea of kind of storing energy, potential energy. So if I lift a heavy object up, so I can lift a bowling ball up from the floor to a certain height. If we think back to like grandfather clocks, so you wind up a grandfather clock not so much by winding a spring to store energy, but by lifting some heavy masses, and as those heavy masses fall, it runs the mechanism of the clock. So gravitational potential energy is basically energy that's stored by changing the position of a given mass. So the work here that's being done is a force of mg is being applied for some height. Okay? So if I go through and realize that that height is really a change in position, initial position minus final position, I can start to think of my potential energy with respect to mgh or mgy in some cases. So your book likes to leave it in terms of mass times gravity times height. I personally prefer to think of it as PE grav as mgy, because I think of it as y positions. So y initial, y final. Because I like to think as the height is that change that you have between y initial and y final. Either way is okay to view it. Some people like the h just because they think the g's and the y's look too similar and it gets confusing. So if you're more comfortable writing with h initial, h final, kind of go with that, or you can kind of go with the y nomenclature. But it's just the mass times gravity, the force, times the displacement or the distance, the height, would be the work. So the actual position, that it's at, the y initial or y final, is going to give us the energy that we have at that particular point. So now our other type of potential is going to be related to springs or rubber bands, things like that, things that have what we call restorative forces on it. So we talked about Hooke's law and how if you take a spring and you stretch it, the force wants to restore it back to its original position, its original shape. Like when you stretch an elastic band, it goes back to its original shape. So stretching an actual spring requires work to be done. Okay? So the work is stored by kind of distorting that material. And that's what we're going to call elastic or spring potential. So materials can have an elasticity if they're willing to distort and then return to their natural state. So with a spring, we normally think of, again, Hooke's law was the force of the spring itself was a negative kx, but the work that we had to do was just kx on it. So if a spring starts as unstretched and I want to stretch it by some distance x, the force that I'm going to have to apply for it is going to go from a force of 0 to a force of kx. Okay? So if we think about that for a second, if I'm going from 0 to kx, well, what's the average force there? Well, it would be 0 plus kx over 2. So that'd be kx over 2, or half of kx. So our average force becomes 1/2 kx. Now we've defined work as, again, force times distance. So an average force of 1/2 kx for a distance of x would become 1/2 kxx, or 1/2 kx squared. So now, since we normally assume that the initial position is 0, so initially there was no energy there, we can think that basically PE spring is just 1/2 kx squared. Again, all just using this idea of work-energy theorem, that the work changes the energy. So again, we have 1/2 the spring constant, basically, K, which the K will be in newtons per meter. So how many newtons of force does it take to stretch it a certain distance, times the distance of that stretch or compression squared. Okay? And that came out of the fact that we had a 1/2 kx as the force, or the average force, times an x. And that's where we get the 1/2 kx squared from. Again, it's still in joules. That's our unit for energy. So now we're going to talk about conservation of energy. So within the universe, energy can transform from one form to another. So it can go from mechanical energy to electrical energy to thermal energy to nuclear energy. Like I said, originally where James Prescott Joule started thinking about energy was the idea of how mechanical energy became heat, became thermal energy. Right now we're just going to focus on mechanical energy in this unit. So when work is done, the energy is transformed from one form to another. So the total amount of universe in the energy has to remain the same. And that's what we mean by the idea of conservation of energy. I mean, there is this really nifty thing, the E equals mc squared that Einstein kind of came up with when working on the photoelectric effect. But still, that statement there states that just an equivalence between conservation of mass and conservation of energy. That mass, because of the idea of nuclear energy, could become energy still. So if energy is conserved, that means that we're never going to be creating or destroying energy. It's just going between one form and the other. So in terms of what we observe, so a frictional force basically takes kinetic energy and turns it into thermal energy. Okay? But if we can avoid having to use friction or calculate friction in, no mechanical energy or potentials and kinetic energies in the mechanical sense will ever turn into thermal energy. Okay? So we're going to define mechanical energy as all the potential energy we have and all the kinetic energy we have. All right? And that mechanical energy, we're just going to call it E for right now. And that E will equal PE plus KE. And by conserving mechanical energy, it means all the energy initial will equal the energy final. It just can change forms. Some people think of this like a bank account. You have savings and you have checking. Savings is your potential, your stored money. Checking is the money you spend day to day. So if I start out with $1,000 between my two accounts, I could have it all in potential, $1,000 in my savings account and nothing in my checking. Well, I could transfer my money back and forth, and I could say, well, I want 500 and 500 to make that 1,000 up. And then, okay, now I've got 500 potential, stored in my savings account and 500 in my checking, my kinetic energy doing something. It's still conserved. I still have it. Okay, I haven't lost it because there's no frictional force there, nothing to make it go away forever, the thermal energy. That's what we mean by conserving mechanical energy. Just instead of dollars here, we're going to be talking about joules of energy. So a couple of great examples. You drop your keys. Keys start out with gravitational potential energy. As they fall, that gravitational potential starts to become kinetic. And right before they hit the ground, they have all kinetic energy. So what was this, kind of somewhat hard 1D motion problem now becomes just setting your PE initial equal to your KE final and solving. Or this interesting problem where what if we had two different shaped slides? And assuming, again, there's no friction. What if you put the two slides next to each other? Which kid would reach the bottom first if they started at the same time? Well, if they start with the same potential, and they're going to end at the same height, they're going to end with the same kinetic, it should take the same time to reach the bottom, but at least at the very least they're going to have the same speed at the bottom because they could take a slightly different path length to get there, but they'll have the same speed at the bottom. And that gets us to our last area, which is power. So power is going to be the measure of how quickly work can be done. So the faster work is done, the greater the power. So power by definition is just the amount of work done in a given amount of time. So work over time is power. So this is joules per second, and that's in watts. And you may have heard the term watts before because of things like light bulbs or power supplies, right? Well, first of all, why do we have the term watt? We'll get to that in a minute. So to be powerful, an engine must produce a substantially, large amount of work in a relatively short amount of time. So if we think of like a car engines can, and we actually talk about horsepower, which has a relevance back to watts. Horsepower is an equivalent power to a horse. So cars with higher horsepower means they can do a lot of work in a small amount of time. So if we want to think of a human, so humans can go run up a set of stairs or walk up a set of stairs. They're going to do the same amount of work, the same change in potential energy. Just in one case, they do it with a short amount of time, a lot of power is being used or being done, or a larger amount of time, less power, okay? So same work, different times yields different power. So where does the watt come from? Well, it comes from a Scottish engineer by the name of James Watt. And what James Watt was trying to do was sell steam engines. And in the time when he was trying to sell steam engines, the Industrial Revolution was just starting out. So the majority of the work at that time was being done by manual labor. So it was being done by people, it was being done by livestock, horses. So one of the kind of major things he was trying to do was sell to coal miners. So in England, a lot of the hard labor of taking coal out of the ground was being done by horses. They'd pull out the carts, and they were running water pumps with carts or tracks of horses that would run a pump. And James Watt came up with this idea that he could replace so many horses with this machine. And the thing with the horse is, well, you got to feed the horse. The horse can't work all day long. It's got to take breaks, or they kind of could become exhausted. So he was trying to find a way to convince these people that his machine, his steam engine, could replace their horses that were doing the work. So he had to come up with a way to convince them. And he decided to kind of do some different tasks with a horse and figure out, well, how much work could a horse do in a certain amount of time? And he came up with a definition of what we now know as a horsepower. All right. So over time, though, they attributed the unit of the watt, that joule per second, to James Watt after this. So Our more familiar unit, the 1 horsepower, is equivalent to 746 watts when we do it out. So if we're thinking of a human can do about 130 watts of power, okay, just walking up a flight of stairs. So it's about 1/6 of a horsepower. If a human runs up the stairs as fast as they can probably peak out around 1/2 of a horsepower for a normal size human. Because again, that's you having to move your mass against gravity up a certain height, certain change in potential. Okay. But again, thinking where people are more used to thinking about power, other than their homes, like electricity, so how much power you're actually using in a light bulb, is cars. So if we think of a watt being work over time, joule per second, we can think of that joule as being done by a force times a displacement or a distance. So if we think of power as force times distance over time, well, distance over time, we actually define that as average velocity way back in our first chapter. So the other way to think of power is a force times an average velocity. So you can think about a car going down the road or going up a hill or something. What is the force times average velocity that's doing? What's the minimum power it needs to do that? Or what power is needed, in some other examples, to accelerate a car, to change its kinetic energy in a certain amount of time. And it's really interesting because, we have cars now that can make 500, 600, or even over 700 horsepower, general production cars. But we've also got cars that have been produced in the past, 30, 40 years, such as, the early Volkswagen Beetles. They were only producing 36 horsepower. That 36 horsepower car can still get up to highway speed. It's just it's going to take a lot longer time because of its power output to do the same change in kinetic energy for the vehicle. So we will do a lot of practice problems with conservation of energy with power with this unit. But again, this is just to kind of get you an idea of what we're going to be using for equations, what some of the terminology is.